everybody. So let's start the second round of the tournament. So at first, I would like to introduce the jurors. I'm Typt from师大. So,
I'm Yuan from Donghai University.
I'm Hanley from Sudan.
I'm Karim from Asia Central University.
So each team with the team leader, please introduce yourself.
We are Team Miracle from 建国高中 and I am 张雅成、徐乐仲、杨佑宇、赖志荣、陈宇俊。
So review.
Hello everyone, we are Team Tesla from 屏东高中 and this is 金善、国浩、罗君宇，我是右希，谢谢。
Hello everyone, this is Yi Chonghan from Charlottetta Junior High School, and this is Chen Yurui, Zhang Yide, Lin Yizhen, and Yuan Xi.
So let's start the opponent. We may start the challenging the question.
We challenge problem 14, ball membrane.
Number 14, ball membrane. Accept. Okay, yeah, so let's start the preparation.
Please write down your name on the board, please.
The reporter, please start.
Hi, I'm Richard from Kingston High School, Children's, and today we're talking about the problem 14, ball on the membrane. So here is the problem statement. When dropping a metal ball on a rubber membrane stretched over a plastic cup, a sound can be heard. Explain the origin of this sound and explore how its characteristics depend on relevant parameters. And we'll main focus on how did the sound got produced and how different parameters affect sound characteristics. So here are the outline. First we'll talk about the observation and this is our theory. And the next will be the experimentation and the last will be conclusion. So here's the observation video and you can see that the ball will create some deformation on the membrane and also it will create a different amplitude and frequency. So we'll try to figure out the relationship between the amplitude, frequency and the deformation of the membrane. So let's talk about the introduction. First, available parameters we'll do is about the size of the balls and different tension of the membrane, and then first one will be the dropping height. And there's some characteristics we'll try to figure out is the amplitude, and we'll use the fast Fourier transform to find the sound frequency. And also the third one will be the collision frequency. So let's talk about the theory. In our observation, membrane has a symmetric elasticity around its center just like this. And you can see in the middle, the pressure of the membrane will be higher, and in the two sides of the membrane will be lower. And also, we can just see this series of like a series of springs, and each spring has a constant that is K1, K2, and K3. And so we can just assume that the membrane has a spring that is a constant of K in the center. And here's the definition of the spring constant. So we use the electronic spring to measure the different constant of the spring. And you can see we just send the same of the deformation, that is the 0.036 and to use the different force to calculate our different constant of the spring. And here is another theory. So we'll think that we can use the standing wave to explain this phenomenon. And so you can see the relationship between the linear and the aerial density is look like this. And the lambda means the linear density, and the sigma means the aerial density. So you can see the lambda equals to the sigma divided by 2. And also we can just conclude that the standing wave formula can change by like this. So the F will be the frequency will equals to the V divided to R. And also the V can change to the root of the F divided by lambda. And also F can change to the constant of the spring times the deformation. So after some calculation, we can just know the relationship between the frequency and this. And about the energy analysis, we can just think that the ball will dropping from the height that is h, and it will rebound at the h prime. And also just like the first one will be the initial energy, and this one will be the last energy. So we can just minus the energy, and we can just calculate the energy that was absorbed by the membrane. And so just can some calculation, we can know that the deformation can write written like this. And we also think that the deformation will be relationship between the pressure variation in this system. And so let's talk about the sound source. So we assume a small accuracy pressure that is P, and the background pressure is P naught. And also we think that it's a compressible fluid flow because you might know that the density inside the membrane will change. And so we use the Euler's equation and continuous equation because we want to follow the momentum and the energy and mass conservation. And also you can see that the rho means the total density, and U is the velocity field, P is the pressure variation. And so you can just think that the P naught is the initial pressure, and the P prime is the pressure difference. So we can just plus these two, and we can know the pressure. And so just like the density and the velocity field. And we just insert the Euler's equation and continuous equation. And so because we want to discuss about the deformation, so we change the density to the relationship between the sound speed and the pressure. And we also just can insert in the Euler's equation, so we know like this. And we also consider the damping because we think that the membrane will not be ideal. So yeah, just add the damping coefficient. And let's talk about the experimentation we do. So here the equipment, so we use the microphone and the sound volume sensor to detect the characteristics of our sound. And we use the balloon holder to change the tension of the membrane. Now we can just change, influence the frequency. And also we use the electromagnetic to release the ball. Now we can just ignore the balls that were caused by our hand. And so it's about the balloon. Balloon, it means we change the balloon means the material of the membrane. And also we use the same plastic top that was the power stem talking about. So here I'm talking about the multiple sizes. So we can know that we use the 10 millimeters one and the 19.06 millimeters one and the 22.23 millimeters one to create different deformation. And about this balloon, we just cover the balloon and also we just fasten by screw by 4 sides of the board, and we just can change its screw of turns so we can change its membrane tension. And here is the setup of our, we need to ensure that the level is the same and is flat enough. So we use the spirit level to ensure that. And here is about the theory of that I talked about. So we think that the deformation will influence the pressure variation, and also we will control the temperature because we think that the temperature will influence the speed of sound. So that might influence some our experimentation results. And let's talk about the first experiment. Is about the dropping height. So you can see that it's the different dropping height from 5 centimeters, 11 centimeters, and 15 centimeters. And let's focus on the 5 centimeters one and the 15 centimeters one. So you can see in the initial sound intensity, you can see that the 15 centimeters one is higher than the 5 centimeters one, and also the density change will like the declining. And just combine all of the data that we have to do. It's about 15, 13, 11, 9, 7, and 5 height. And you can see that the 15 centimeters one will always higher than the other, like 13, 11, 9, 7, and 5. So we can just conclude that if the dropping height is higher and the collision frequency will be lower. So we also use the fast Fourier transform to find about the peak frequency. So you can see the frequency is the same, that is the 257.8, because we think that the thing that will influence the frequency is about the tension. So that might be reasonable. And let's talk about some discussion. So the first is about the amplitude. You know that the amplitude is lower as the rebound times increase. And also the initial height is higher. You can know that the initial amplitude is higher. And the second is about the collision frequency. You can just know that if we drop the ball higher, and also the frequency will be lower. And the third one will be the peak frequency. Just like we use the fast Fourier transform, we can just know the results. And the second experiment will be the size of the balls. So here's the 11 centimeters of the dropping height and about the small, medium, and large ball. And here's the 15 centimeters one. So we combine the 2 different dropping heights and 3 different sizes of balls. You can see that the large ball of the 11 centimeters one is the 127 AU and medium is 113, small is the 105. And so we can just know that the large ball will always have a higher intensity of the sound than the medium ball, than the small ball, and just like the 15 centimeters one. And we also do the fast Fourier frequency to find the peak frequency, so we can just know that also the frequency will be the same, and the reason is the same, that is the tension of the membrane is the same. And let's look at some discussion. So you can see the amplitude. The amplitude also will be the ball sizes. If the ball size is bigger and the initial amplitude will be bigger, you can just think that the deformation also will be bigger, so that causes the amplitude larger. And the second will be the ball size bigger and the height higher. The sound between the collision will be higher, just like our experimentation results. And the third one will be the peak frequency will almost the same, because just like we have talked about, the tension will be the same. So the tension will influence the frequency. We can just know that. And the third experiment was talking about the tension of the membrane. So here are the thing that we have to do before, just because we can change the constant of the spring, and also know that the tension is higher, sending wave frequency will be faster. And here's the data that about 3 turns, and the frequency will be 257.8. 4 turns will be the 275.3, and 5 turns will be the 339.8. And so we can just discuss some phenomena. So we can just know that tension higher and the frequency will be higher. Because if we change the constant, the tension of the membrane, we also will change the constant of the spring. And you can just think that the frequency will be higher when we have more turns of the screw. That means the tension is higher. So we can just know that if the tension is higher, also the frequency will be higher. And let's talk about some conclusions. So the first one and the second one will be a theoretical conclusion. So we can see that the first one is talking about the pressure variation will caused by the metal ball. And you can see the third one. If the dropping height is higher and the size of the ball is bigger, that will form a deformation value higher. So we can just know that the deformation and will cause the amplitude higher. Then the second will be the frequency change the sound. That means we can see the phenomenon as a standing wave frequency. Let's look at this and just like the fourth one. If the tension is higher, that will cause the higher pitch about the frequency. Because we can know that the tension is higher, the K will be higher, and also we can just influence the frequency of the sound, and the frequency will be higher. And here are the reference we have used, and this is my report. Thank you.
So thanks to the reporter for his report. Can you go to page 7? So why do you approximate the membrane as a series of springs? What's your intuitive justification for this?
I think that different parts of the membrane have a different constant of K, but we can just think that the center will be the thing I will discuss about because we just jump on the center.
Can you go to page 9? So why can you use this relationship for the standing wave formula? How did you generalize it into the 2 dimensions?
Because I just think that we can just think that the surface of membrane as an areal density, so we can use this theory about.
But the K constant will be different for different regions of the membrane. You said that it is made up of a series of springs with different spring constant. What's the K value for your experiment?
I think what I'll talk about will drop in the center, so maybe the constant will be the same if we don't change the tension.
Okay. Can you go to page 13? So you mentioned the damping coefficient here, and I don't really see you using this entire formula. Did you use this formula to explain anything in your report?
We just think that we can just add the damping. So yeah, maybe we don't use a lot.
What did you use the formula, not just the damping, the entire formula in your
formula
theory?
We just can look at the pressure will change by So we can think that the pressure change will influence the deformation.
So this is just to say that the pressure change will, what's this formula trying to explain?
About the pressure change will change our experimentation.
Okay. So can you explain in one sentence where the sound comes from?
Do you think? I think it comes from the air under the membrane.
Okay.
competitors. I am Zhang Yaocheng from Team Miracle, and I'll be posing problem 14 ball on membrane. So the problem statement says that when dropping a metal ball on a rubber membrane stretched over a plastic cup, a sound can be heard. Explain the origin of this sound and explore how its characteristics depend on relevant parameters. And so the reporter says that the origin of the sound is that the vibration of the membrane causes the pressure of the air under the membrane, which produces the sound. And for the characteristics, they analyze the frequency and the amplitude. Okay, and for their theory, they approximated the membrane as a series of springs, and they used the Euler's equation and the continuity equation to explain why the vibration of the membrane causes the sound here. And for the overview of the report, they approximated the membrane as a series of strings, and they calculated the vibration. They assumed the frequency the membrane will produce would be the oscillation of the standing wave of the membrane. And they also analyzed the energy of the ball, which they analyzed by looking at the height change that the ball dropped from. And also they used the Euler and continuity equation to explain the sound here. And for the parameters, they changed the tension of the membrane by stretching it. And their result is that when the tension is higher, the frequency they hear will also be higher, but they have no quantitative explanation for this or a comparison between their theory or experiments. And for the drop height, they said that for the higher drop height, the amplitude will be louder, but the frequency doesn't change. And for the size of the ball is the same as the drop height. For a larger ball, the frequency stays the same, but the amplitude is different. And here are the pros and cons. The reporter has good time management and he has concise explanation and graphs. But for the cons, there's very little comparison between his theory and his experiment. And I would think his theory is quite unpersuasive because as I said, there's no comparison. And there's the unclear explanation for the origin of the sound. For example, did he verify that it comes from the resonance of the container, or does it actually come from the vibration of the membrane? And he changed two variables at once. For example, changed the mass of the ball and the size of the ball at the same time. And it doesn't explain the coupling coefficient, K, and the damping coefficient in his experiment, and he didn't verify many relationships that he proposed. So the points to be discussed, I'll focus on some of the relationships he proposed in his explanation, and the meaning of the frequencies he detected. And for experiments, I'd like to ask which part of the audio he took, and that might influence the experimental results. Also, we want to discuss how the shape of the container will affect the frequency we detect. So we would like to begin our discussion. So, reporter, can you go to page 19? Okay, here, did you verify this relationship here with your experimental data?
I didn't verify it, but we can just see that the information.
But this is the information. I think this is actually quite easy to verify because you only need to take the relationship between. You only need to get the data from the change of the height of the ball and the deformation of the membrane, which you can easily get with the camera. Can you go to page 37? So, yes, the same thing is seen here. Did you verify this relationship, or is this just your qualitative explanation for the change?
Okay. So we just know that different constant will change the frequency.
Also, this is just to say that the different constant will change the frequency.
Yes.
It's not to provide a quantitative explanation.
Yes.
Okay, and you didn't verify how, like, the tension that was caused by in terms of the screw. Did you measure the tension?
Mentioned in the. Here, but change the terms of screw and have the different code.
Oh, okay, thank you. And can you go to page, nope. So, I'd like to ask you, which part of the audio did you take? Like, did you take the audio from the collision of the ball with the membrane, or did you take the audio from after the collision, the ringing of the membrane?
Maybe you would use this after collision.
After the collision. Do you think that if you took the audio from the collision, the result would change?
Yeah, might be some change around, yeah. because the sound will be not very have an order.
Will change. How do you think that will change? Do you think the frequency will change, or do you think the amplitude will change?
I think it's about the amplitude.
You think it's about amplitude? Okay, we'll discuss that later. And do you have any theory to describe the peak frequency you detected?
We don't have any theory, but we use the fast Fourier frequency.
Yeah. So that's your experimental data. But do you have any theory to explain the peak frequency? Can you go to your data showing the fast Fourier transform? Yeah, so what is the meaning of the peak frequency? Is this the base frequency of the membrane, or what is this here?
That means the main, you can see the main sound of the intensity level is peak. To find that is the peak frequency.
Main
It's like the highest intensity of the sound.
But you don't know what causes this main frequency. You don't know what this frequency comes from.
I think it just comes from the we are talking about the membrane touch the membrane the ball touch the membrane and of course the sound under.
Oh, so you think this comes from the membrane?
No, it comes from the membrane and membrane will just wave, so it cause the air under the membrane will move.
Okay, so can you explain the frequency? This, yes, can you explain other frequencies? What do these small frequencies mean? Are these just noise or are these actually data?
I think the first is the highest. You can see highest, and highest. The highest means the first the ball touch the membrane and will cause the high, and you will just move the air, so the air will be lower than the other.
But you just said that you took the audio after the collision. How could this be caused by the ball touching the membrane if you took the audio after the collision?
Just like the ball just left the membrane and you have caused the membrane moving. So I think it's about that.
So you think these are caused by the different stages of the vibration? These are not caused all at once?
Yeah, not at once.
Not all at once.
You mean at once is that the same?
Like these appear all at once. They don't appear like this doesn't appear first and then this appears and this appears. They appear all at once.
You mean just like the whole experience, the chamber like look like this?
No, I'm asking you if these two frequencies can exist at the same time, or
yes. You can see we just use the fast Fourier transform, so we can just separate the different frequency of the sound. So
yes, but you don't know if they exist at the same time or they exist like this appears first and then this appears and this appears. You don't know which one appears first.
Yes.
Okay. So do you think that if you took the fast Fourier transform of the frequency for different times, the result will be different?
You mean different types of the experiment?
Yes.
I think it will not be different because we have talked about that the membrane will change the tension that cause the different frequencies.
So you think this will not be different?
Because we think that the main focus, the influence will be the tension of the membrane.
Okay. Do you think that the amplitude will change if you took the different times of the audio?
That will change, but yeah, we can just because you can just know that the energy will lost, so the amplitude will change.
But do you think that the height of the peaks would change? Like this one will become smaller and this one will become taller than this peak.
To change one, that would cause
that you have like a primary peak here and a secondary peak. Do you think this secondary peak may become larger than the primary peak?
I think it won't be higher because the first time we drop the ball will be the highest, the biggest energy that caused on the membrane.
Okay, so you think this will remain the largest peak throughout the entire.
Yes.
But because this is a very large peak, it means that energy dissipates from the membrane very quickly.
Yes.
You agree? So if energy dissipates from the membrane really quickly for this peak, then it means that it decays really quickly too.
Yeah.
And that means that as time goes on, this peak will decline more quickly than the second peak. So do you think now that the second peak may become larger than the first peak?
You mean the decline will be
faster because its amplitude is bigger,
yeah.
And that means that the energy dissipation from the membrane is also faster because we hear a louder sound. You detect a louder decibel. A louder decibel means that energy dissipates from the membrane for this frequency faster. And that means that the energy decay for this peak might also be larger.
Yes, larger, and the rebound will not be larger than the first one, I think.
You still think this will not be larger than first peak?
Yes.
Okay. And now I'd like to move on to another discussion. How do you think the shape or the material of the container will influence your experimental
You
results?
mean the physical size?
Yes, yes,
That will change the air under the membrane, right?
yes.
So I think that will cause the different pressure of vibration, because you can think that if the air is we have more air, then that will cause the pressure less.
If there's more air, do you think that will change the amplitude or the frequency if the length of the air is changed for your
So
container?
let's talk about that. Deformation will change the amplitude, right?
Yes,
So did you agree with that?
yes.
So I think that the main influence will be the deformation and also the deformation that cause the pressure variation. So I think that's just about the right pressure. So we can just think that we have a larger Pascal, and then maybe the pressure will be lower.
But how would that influence the frequency or amplitude?
I have talked about the frequency. I think it's about the tension of the membrane.
So you think that changing the length of the air column or the changing the height of the
Or the both sides about the amplitude change.
the length of your container doesn't change the frequency because it is determined by the tension of the membrane.
Yeah, I think that is.
Okay. But do you think that will change the amplitude distribution?
You mean the size of the test?
Yes, yes, yes.
Yes, that will change the amplitude distribution. We can think that the air will. Yeah, the air will have more pressure if we have a higher height.
Yes.
Or, yeah.
So do you think that maybe if you change it to a different length, the second peak here might become larger than the first peak, or maybe it would cause some amplitude
You
change?
mean I change the frequency curve, or will the different second will be higher than the first one?
That's just a metaphor. If you change the height of the container, how will the frequency profile change?
So I think that the main will be the height of the dropping height. So maybe if we have set the same dropping height, the sound will maybe not change.
You think so? So you think changing the length of the container doesn't influence the sound of your member, the sound you
I think that's right, because I think that I talked about the pressure variation, right? So I think maybe pressure variation will change the energy of the sound. So yes, that will cause the different pressure. So that causes a different amplitude.
amplitude. So also that will change the amplitude.
Yes, about the pressure variation.
Okay. So maybe the sound you hear with a 5 centimeter container will be different than the sound you hear with a 10 centimeter container.
About the amplitude.
About the amplitude.
Yes.
Yes. So the tone you hear will be different.
Yes.
Okay. And how do you think the material of the container will affect the sound? Do you think it's trivial, or do you think you have to take it into consideration?
I think you can just think that if the sound will go out about the container, and that can cause a smaller pressure of the air. The sound just
the material, the shape of the
about
container.
if you use the container that will just let the pressure go out faster, and that will cause the different experimentation result.
So the material will cause a difference.
Yes, so
Okay.
it's the same method as plastic.
Okay, thank you. So that's all my discussions.
Thank you.
Okay.
So start in the summary.
And in our discussion, we discussed several relationships the reporter presented, and we found out that he didn't compare his theory to experiment. He used the very complicated equations to explain some very intuitive phenomena. For example, that the vibration of the membrane causes the sound we hear. And we then move on to the discussion of whether to the meaning of the different amplitudes. And the reporter says that all of his amplitudes, all of the peaks of the amplitudes can happen at the same time, and they may change according to time because some peaks may decay faster and some peaks may decay less as fast. So we think that the reporter could take the audio from different times to see how this changes and how this affects the sound we hear. And then lastly, we explored how the container might affect, and the reporter agrees with us that the container will affect the sound we hear.
Yeah, so the time for the reviewer.
for the reporter and the opponent. The first question I want to ask for opponent. You asked the reporter about that you can see the membrane as a series of screens. Then what do you think about the membrane?
I can't see. I didn't say that you can't see the membrane as a series of screens. I asked the reporter for an intuitive explanation.
Okay. And another for the reporter. Will the constant K of the screen or membrane be the same over time?
So we change the tension of the string membrane, so that will cause different things.
Okay. Again for the reporter, how does do the pressure influence the frequency, or it does only influence the intensity? Or
So I have mentioned about that the frequency will only change by the tension of the membrane, and also that will change the attitude because it will cause the different air pressure variations.
okay. For the reporter, do you think that the frequency you use fast Fourier transform to investigate the phenomena? So do you think the frequency of each drop will change over time?
Well, I think you will just have the highest frequency, and maybe that will change over time, but we can just like the opponent said, we have to see the result at one time. So maybe we can just discuss in the future.
Okay. So for the opponent, what do you think about will each collision influence the different amplitude or frequency?
You mean changing the?
No. Like the first drop and the second drop.
From the reporter's report, he says that the height doesn't influence the frequency. So from his data, I have to conclude that it doesn't affect the frequency, but it affects the amplitude.
Okay. For the reporter, do you think the ball's mass or the ball's volume affects the sound?
So I just we use the different size of balls, and that will cause the different deformation. So I think the main will be the deformation of the membrane.
So you use different sizes of a ball. So does the volume or the mass influence the sound?
You can think that the mass will cause a higher deformation, right?
Yes.
So I just think that if the mass is higher, and also the deformation will be higher.
Okay. For the reporter again, do you use other membranes instead of the balloon?
You mean we have changed the membrane?
Yeah.
We have just changed the membrane each of the time because we think the membrane will maybe the fatigue.
Oh, okay. How do you avoid the noises of when you're?
You can see our equipment. We have used the soundproof box, so we can just ignore the sound of the noise.
Okay, then that's the end of my review.
Thank you. So it's the time for the preparation of reviewer. So the reviewer, please take the floor.
Okay, this is the problem statement, and I won't repeat it again. Okay, so I want to talk about the performance of the reporter. First, they use theoretical models by literature, use many functions to try to prove, and they understand quite a lot of series and consider a lot of parameters, for example, the height and the mass. So they use how to accurately get rid of other forces that will affect the experiment, and some interesting founds that we can see, and answer the questioning of methods fluently. But cons, they fail to accurately explain the use of functions, and they did not mention a lot about the series, but not exactly how they calculate. And the report should be more focused on data statistics instead of over-analyzing. And the theory, as the opponent said, is not really persuasive. Okay, so the performance of opponent. They specifically ask the key methods, and they question the use and apply of the formula. But for the cons, they talk too much about unrelevant points of view. But in this test, I think what we need to do is to really think about investigate more on the sound and amplitude and frequency. Okay, so this is the discussion topic. The opponent asks how different K on the membrane and different materials of the cloud will influence the phenomena. And in my view, we also consider different types of membrane that will influence the sound. And as for the K on the membrane, it is essential for us to think about it again, because the K we think will be different of different places on the membrane. Okay, so the opponent also asked where exactly does the sound come from, and the reporter said the sound comes from inside the cup, but we think the air that vibrates through the motion is also, we can hear the sound. And we need to more specifically discuss about the timing when the highest peak is caused in a single movement. Okay, this is our point making. No investigate on different sound of different collisions. For example, the frequency we think may be different of different collisions, and that may be essential for this experiment because the amplitude, not only the different collisions influence the amplitude, the frequency, they use FFT, but we don't know what exact time of exact frequency. So maybe that's what we can do in further experiments. And that's the end of my review. Thank you.
Okay. So the concluding remark from the reporter.
So thanks for the opponent and our the reviewers. They gave me a lot of advice about this experimentation, and also we have talked about the amplitude and about the frequency change. So I think that the amplitude will change by the different height of ball or the different size of ball. So that will cause the different deformation and will cause the amplitude change. And also about the frequency, I think that the tension will influence the frequency of the sound. So just like our experimentation. And all in all, we have learned a lot about this formula, and I appreciate the opponent and the viewer for a great discussion. And we also just can do in the future is about the opponent said that about the fast Fourier frequency uses. We can use how to use this to explain our phenomena more clearly. And also we can just we should do more about the different size of the container to ensure the relationship between the size and the amplitude, because the opponent has said that we can change the size of the different, like the material or the height of the plastic cup, and that will change the different pressure under the membrane of the air. So that might be the one thing that we can just influence the sound of that caused by the membrane. And so here's my remark. Thank you.
Okay, time for the jurors.
I want to ask a simple question to clarify the problem. Okay? If we only consider the dimension of the membrane, means the height of the cup or the diameter of the membrane, we change these two parameters, what will happen in the sound you heard, or the frequency or amplitude?
So I think if we change the membrane, like the radius of the membrane, the larger, that will cause the pressure of the air lower, so that will cause the amplitude lower.
So
Because
when you see the amplitude.
Yeah, you can just think that the force will, yeah.
Okay.
We think it will influence both the frequency and the amplitude, because
if the dimension is larger or smaller.
The opponent thinks that if the dimension of the membrane is larger, the amplitude will shift to a lower the frequency will be lower. And for the amplitude, we think that for a larger membrane, it has to depend on its spring constant. And if the spring constant is really large, then the sound we hear might be louder because the area is louder. But if it's really small, then it will just sink downwards, and we won't be able to hear a loud sound.
I think the influence the sound is about the K of the membrane, and also you say that the dimension and the diameter of the membrane. So the cup's diameter and the air will change over time. It will change. Sorry. So it will also affect the phenomenon, the sound that we heard.
So the amplitude or frequency will any change? Any change in the amplitude or frequency?
Yes, it will change in the amplitude and frequency. For amplitude first, I think that it will decrease. If the height is the same, then the amplitude it will decrease when we expand the membrane.
Okay. So from the Fourier transform, so you see multiple peaks, right?
Yes.
So what does that mean?
So I think that the first peak will be the collision that cause the membrane move, and the other will decrease. That means the air will just moving but will decrease because there will the energy loss.
Well, but there is another. You see that there is a primary, a second, and third. There are three major peaks. So what does the other mean?
I think that might just about maybe the maybe just like if we have more pressure vibration also will not be right down just like linear, so maybe we just have changed the pressure. It's like the membrane will move, so they'll change the pressure of the air under the membrane. So that will cause the pressure change, but not the linear change.
Can you comment on this?
For the two peaks. For the two peaks.
For the three major peaks.
For the three major peaks. First, the frequency, if you report it for maybe 10 seconds, for example, then the frequency. This graph is about the all frequency and intensity in the 10 seconds. So, so you can see that the the larger peak is about the membrane is sound, and for the last two peaks, I think it may be about the air that's come from the inside of the cup and the air.
We think it's because of the different vibrational modes of the membrane. Yes.
Okay, so is there any further question? Then the story time. Okay, so please come. So for the reporter, six, 8, 7, 8. For the opponent, 8, 7, 8, 8, 8. Quite tough difference. So for the reviewer, 7, 8, 7, 7, 7. Yeah, very consistent. Okay. So let's take a 10-minute break. Start the second part of today's tournament. So let's start with the challenging the question.
Yeah, so we would like to challenge question number 13, Kendall power turbine.
Okay. Question number 13, Kendall power turbine. The third. So the question number 13, Kendall power turbine. So please write down the name of the reporter. 这里的电脑。
有，我其实已经有回来了，就是昨天那个，昨天那个看没有打，
而且上面
照片好。
有变大了，反正中间重点是看到这个。
I would like to begin my presentation. Okay. Good morning, dear judges and fellow competitors. I am Jaya from Team Miracle, and I will be presenting problem 13, candle power turbine. So the problem statement says that a paper spiral suspended above a candle starts to rotate. Optimize the setup for maximum torque. And we think there are three key questions. Why does the spiral rotate? What are the parameters affecting the torque? And how can the setup be changed to achieve maximum torque? And this is our table of contents. So first we'll show you our phenomenon, a video demonstration. And then we will develop our theoretical model with the kinetic theory of gases. And then we'll move on to our experimental setup and our Schlieren imaging. And then finally we will move on to our experimental analysis of the angular velocity of torque, followed by the conclusion. So here's a video showing the phenomenon. And as you can see, when the candle is lit, the spiral starts to rotate. And you can notice that we kept the shape of the spiral with an aluminum wire. So the air rising from the candle flows through the spiral turbine, pushes against it, and making it rotate. The spiral converts part of the kinetic energy of the flow into its rotational energy. And in order to develop our theoretical model, we have to look at the flow field of a candle. So for the flow that is close to the flame of a candle, the flow is laminar. And the width of the flow is relatively constant with the height. And for the turbulence flow, it occurs at a higher at a height that is further from the flame of the candle. And also you can see that there's the air influx that is replenishing the air that is risen to the top. And to develop the theoretical model for the flow of the laminar region, we use the equation of continuity and the momentum equation and the energy equation. Gamma here is the heat capacity ratio, and lambda is T1 over T naught, and that is the temperature after divided by the temperature before combustion. And combining these three equations, we get the velocity of the flow field, to the ratio of the velocity to the flow field, to the velocity of the intake air. equation, and that is equal to this right here. And m is the Mach number. And if we consider the flow as an ideal gas, we can use the kinetic theory of gases. And the momentum a spiral receives is 2us times cosine alpha. That is the momentum here. And cosine alpha can be calculated by the vector of u here and the normal vector of the spiral. And as you can see, the most important component of the vector of n here is n3. So how do we calculate n3? First, we have to define a spiral. And in order to define the spiral, we have to use parametric equations. So S1 is the parametric equation for the first spiral band, and S2 is the parametric equation for the second spiral band. And because we're using an Archimedes spiral, R1 is equal to k times theta, and we'll be calling k the spiral constant from now on. The height is equals to t theta. And for the second band, R2 is equal to a plus k theta. And a is the radius of the first band. And its height is b plus t theta. B is the height from the top of the spiral to the top of the second band. And as you can see, delta here is the tangential vector of the spiral. If you take the cross product of R and the unit tangent vector, we can get the normal vector that points outwards. And so we calculate the unit tangent vector with the parametric equation, and that is equated here. We then take the cross product of R with the unit tangent vector to get the equation for n3. And because delta B is equal to n3, it is also proportional to, because delta B is proportional to n3, it is also proportional to this here. And in our experimental setup, we use Schiller and imaging to identify where the flow turns from laminar to turbulence. And here's the video showing our experiment. And as you can see, the flow actually turns from laminar to turbulence at this point here, this height. And that is about 18 centimeters from the top of the candle. Okay, so for our experiment, our control variables are the diameter to height ratio of the Archimedean spiral. And we also control the power of the candle by keeping the wick length, the part that's burning, the same. And for our operational variables, we change the horizontal distance from the candle to the center of the spiral. And we also change the vertical distance from the candle to the spiral. And finally, we change the spiral bandwidth. And to analyze the motion of a spiral, we use this equation here. And kappa is the torsion constant of the string, which we measured with the angular oscillation. And B is the damping coefficient from air resistance. And in order to measure the damping coefficient from air resistance, we use the stepping motor to spin the spiral until it reaches its maximum velocity. And then we stop the stepping motor and we calculate how much the string has turned. And using the torsion constant, we can calculate the force that the air resistance acts on the spiral. As a relationship, as a function of the rotational velocity. So this is a graph showing the torque to rotational velocity. And as you can see, it is approximately linear. So here we confirm that the resistance from the air friction is linearly proportional to the rotational velocity. And we also got the value for V. And for our experimental setup, we use aluminum wire to keep the shape of the spiral, and it's an Archimedean spiral, and the wick length is 5 millimeters. Okay, so the candle is placed between the middle of the spiral. And this is the rotational velocity to the height, that is this distance here. Relationship graph. And this is the torque. And as you can see, the maximum torque actually occurs at the turbulence section of candle flow. And that's a really interesting phenomenon. But remember, the candle is placed right below the middle of the spiral. And for the horizontal distance, you can see that the torque reaches maximum at about 2 to 3 centimeters from the center of the spiral. And for the spatial geometry, we change the spiral constant. And as a reminder, this is the relationship between the radial vector and the spiral constant at theta. So for a smaller spiral constant, the bandwidth is thinner. And for a larger spiral constant, the bandwidth is thicker. And here's the relationship showing the rotational velocity to the distance from the center of the spiral to the candle. And as you can see, for a larger spiral constant, the torque is also larger. And that is, we can tell that by the larger rotational velocity here. And for lower spiral constants, the torque is lower. And we think that is because for a smaller spiral constant, the bandwidth is also thinner. So there are more gaps for the air to pass through without actually providing torque to our spiral. And there are several possible places for error. And the first is that the turbulence is too complicated to quantify. And also, the flow is an ideal gas, so we wouldn't be able to exactly apply our equations to the spiral. Also, the flow turns into turbulence when going through the gap between the two paper bends. And that affects the torque on the outer spiral. Also, there may be quanta effect. So in conclusion, the flow of the candle pushes the spiral and turns it. And to achieve a larger torque, the spiral has to be placed in turbulence if it is at the middle. And that is because for a laminar flow, most of the air is concentrated at the center. And the distance it can act on is very, very small. So the torque is also very small. But if it expands into turbulence flow, then the distance it acts on becomes larger. And so it can provide larger torque. Also, if we offset the pendulum by 1 to 2 centimeters, the torque we provide, is also largest. And when there's less gap between the spiral, meaning a larger spiral constant, the torsion on the spiral is also larger because there's less gap for the air to escape. And here are our references. That's our presentation. Thank you.
The opponent, please ask the question.
Okay, so thank you for your report, and I really appreciate your work. Okay, so first question I'm going to ask you, I'm curious about your experimental setup. Like, for example, how do you draw or cut your candle turtle?
Oh, we use we print out the line for the Archimedean spiral, and then we cut it with a scissor.
Yeah.
And then we attach a wire. We have a mold that we shape the aluminum wire so that every single aluminum wire is the same, and then we attach that aluminum wire onto the paper spiral so it keeps the shape of the spiral.
So you mean that you put the wire on the spiral when you do the experiment, right?
Yes, you can see for this video, the wire is placed at the middle of the band.
Yeah.
And it helps keep its shape.
So I remember that the question it says only about the paper spiral. So wouldn't the wire affect the motion or something else?
That's a good question, but we think the wire only affects its rotational inertia. And the reason we keep them, the reason we have to use a wire is that if we let the paper droop on its own, then it is very difficult to control the length from the candle to the spiral because it deforms very easily, so we cannot control the height from the candle to the spiral, and that influences torque.
Okay. So you talk about in formula about the energy equation, and can you talk about more about the function?
You mean talk about more about the three functions?
Yeah, the energy equation. Like what parameters do you consider, and how do you calculate and take it into consideration?
If I were to take into consideration, for example, let's look at lambda here because that's the relationship between the velocity of the combustion flow and the velocity of the air intake. If lambda is larger, for example, if our candle is starting to burn hotter, then the velocity of the laminar flow will also be larger. And also, if our air supply intake is larger, then the velocity of the combustion flow will also be larger.
Okay. Yeah. So give preparation time. Okay, the opponent, please take the floor.
Okay, so I'll start our opposition on problem Kendall power turbine in our team Tesla. Okay, so this is a task and it requires a reverse spiral and optimize the maximum torque. So I just get it over. Okay, so the structure of the reporter from solving the problem, why does the turbine rotate in different parameters and when is the maximum torque? Okay, so the report, and we believe that they have a theoretical model and simple understandable qualitative explanation torque and appropriate use of media. And but we believe that the cons are the lacking explanation of parameters and missing investigation of the flow of the candle and the complete investigation of candle power. In their experiments, they have accurate and reproducible setup and test of randomness, but they have no connection between the theory and experiments, and no measurements of maximum torque and missing investigation of the power of the candle, and not enough experiments, which I believe, and the line will move in complete experiments influence. So here are the points of discussions that I will go over through my questions with the reporter, which the turbine is the fastest, and what external influences changes the effective torque, and how to measure the torque on the turbine during the experiment, and different kinds of spiral. Okay, so I'll start my discussion with the reporter. Okay, so in the front of the report, you mentioned that we have to get the angular velocity of torque. And so I would like to ask you on page 4. Yeah, the experiment page 4.
Page 4.
Yeah. So how do you actually keep the spiral on
You mean how do I keep the spiral?
on the pin,
You mean
on the stick.
it's not, and there's no stick here. There's, you can, oh. So there's a line that is hanging on a spiral.
Oh. So, and I would like to ask you to turn to page 7. Okay, so I asked you to explain more about the energy equation first, and I have a question there. Like the US over UV, like last line of the equation, like how do you get the number from your experiment?
Well, we cannot get the number from our experiment, but this is a qualitative experiment. This is a qualitative analysis of the laminar flow from the candle. So we did not apply this exact function to our experiment because we kept the wavelength the same and we didn't change the air.
Then why do you mention this function?
Oh, so this is just to tell us that we can actually quantify the flow from the candle. And there are, yes.
Okay, and then how about the 3 functions from the top? Like, can you apply like one of those in your experiment data?
Well, can I apply one first?
Yeah, okay.
No.
No?
No, we need to combine these 3 equations to get this one. We cannot just apply each one individually.
So why the line? Why do you combine the 3 functions for the line? If you cannot?
Oh, because there are a lot of variables here. You know, in order to calculate the torque, we need the momentum, so we cannot just use the equation of continuity. But there are many variables. For example, ρ1, ρ2, and there's also the variable of pressure, and there's also the variable of the flow velocity.
Yeah.
So we cannot just use each. We cannot just use one of them.
Okay, so the combination, you use the function to design your model or your experiment. Did you?
Design our model.
Like, I don't actually know what that thing is for.
Oh, so this tells us that, okay, so it tells us that the firepower from the candle, the heat after combustion and before the combustions, can cause the flow velocity, and which this can cause torque on our spiral. So we kept the wavelength the same. We're keeping this the same. So our velocity from the candle is also controlled.
How do you control?
We kept the wavelength the same. For example, you can see here that in our control variable is that we kept the power from the candle the same. We kept the wavelength the same.
Okay, so do you consider about like the power of candle?
Consider the power of the candle.
Like for example, how big the candle is and like how hot the candle will.
No, we did not change that in the data we presented.
Okay, then I have another question about, like, you used the model for the Archimedes turbine, right? Okay, and I believe that the Archimedes turbine is not the exact model of the turbine because it's like two ways and 2 sides. So do you mean that you just cut down the Archimedes turbine like into a single rotation?
Do you mean I cut down the? Can you draw what you mean on the blackboard?
Okay. So I believe that the Archimedes wind turbine, like our candle turbine is like a single window. And I believe that the Archimedes turbine has a novel window. So it's applied for the wind turbine, not for actually the fluid of this.
What do you mean?
Like this is a sorry, I'm poor drawing. So that's the example, right? So like the Archimedes turbine is like this, so it has not in another side of it.
There's no.
Making it straight.
I'm really poor drawing. Okay, so our Archimedes spiral is like this, and then
Yeah.
all we did was find a spiral function for this, and if we cut this along the line here, then we only get one spiral. I'm not sure what you mean that we get 2 spirals.
The Archimedes turbine is just an actual spiral, and it is not like it's full inside, right?
We use this function because it is clearly defined, and it is easier to calculate in our mathematical analysis.
Yeah.
So we just chose this function for our spiral.
Okay, so like it's just for the calculation of the Archimedes, like not.
Yes, it's just to define a spiral.
Okay. Okay, then can I ask you to turn to page 8? how do you explain the graph stand for me? Like, I don't actually.
Okay, so
Like, there's another for me.
a spiral will look like this here, and there will be like a slope, and there will be a normal vector. And because our air rises up and contacts the spiral, and because it is kinetic, we're using the kinetic theory of gases, it bounces right off, and it provides an impulse in this direction. So the delta P there is just the impulse, and this is the angle alpha here. And only the component that is parallel, the velocity component that is parallel to the normal vector matters. So we have to multiply 2u by cosine alpha. That is the simple.
Okay. Then can you predict how the paper turbine will turn? Like if you.
Can I predict how? You mean with a theoretical model?
Yeah. Like if you like the gas molecule is there, and so if you put the candle over there, then can you predict how the paper turbine will turn?
No, not exactly, because there will be turbulence from the rotation of the spiral, and also because the spiral is rotating, the impulse won't be just calculated like this. You cannot just calculate it like this. But this tells me that if the spiral is spinning, you can calculate the impulse, and the parameter we need to control here is that N3 stays the same. So we're using our aluminum wire to keep N3 the same throughout our experiment. So this tells us that it is important to keep the shape of the spiral and not let it droop down on its own, because it changes the shape, it changes the impulse it receives.
Then, so like actually like on the problem that the question doesn't requires that you have to put a spiral in the shape. Yeah,
Yes.
but the whole of your experiment in your theory you use a wire.
Yes.
Yeah, so okay, so I'm gonna discuss about how if you take off the wire, then how do you think would the candle decrease its length over time?
How will I think?
How do you think the candle will decrease its length or like its bounce or something? Like how often do you have to change the candle?
How often do I have to
Do you
change?
think?
Well, for our experiment, it actually burns for approximately like on a scale of 1 minute, maybe 1 minute to 2 minutes. So the height it changes is on a scale of millimeters. So the change of height is very, very small for the candle. And we switch out the candle for every experiment.
Okay. Then like overall of your report, and what do you think the maximum torque of the is?
Okay. So if the candle was placed directly under the center of the spiral, then you can see here in our torsion graph, then the height from its width to the spiral should be about 24 centimeters, and that is longer than our length, than the height which the laminar flow turns into the turbulence flow, which is 18 centimeters. So it has to be in a turbulence region, and for our experiment that is 24 centimeters. And our explanation is that because when the laminar flow turns into turbulence flow, it expands. So there's more, the distance the axon is larger, so the torque is also larger. And if the height is, and if the height goes down for larger volumes, then the torque decreases because there's more energy dissipation, and it is also harder to because there's energy dissipation. Yeah, that's it.
Okay, so I'm gonna ask another thing about your experiment setup. Like you said, you put a candle above the turbine above the candle for about like 18 centimeters. And how do you keep the experiment set up like without any other influences?
You mean? Oh, I don't keep it just at about centimeters, at 18 centimeters. One of the parameters is the height. And you're asking how I keep the other parameters. Can you elaborate on that? What do you mean by other parameters?
Like the whole experiment setup, and how do you keep that there isn't other influences about your experiment?
Also, we keep this in the corner of our experimental lab, so that and when we're conducting experiments, we usually close the door so that there will be like we can close the region and leaving a space at the bottom for the air to flow in. But as you can see in our video, we also don't walk around too much, causing turbulence from our motion, and that is how we control the airflow of the region, like this. And the height is controlled by this string here.
Okay. Okay. And then ask another question. And like when you use different kinds of spiral, then how do you match your shape from different kinds of spiral?
You mean if I use different kinds of spiral?
Yeah.
If I use different kinds of spiral, for our experiment, we will conclude that if the spiral has a thicker band, then we think the torque will be larger if it has a thicker band. Yes. And the spiral also has to be symmetric to the center, so that its mass does not swing from side to side because of rotation.
Okay. Okay, so about your wire, then have you ever considered that the lines, that the wire's tension would change?
You
Or
mean,
like it would have some like chemical reactions with the fire?
you mean this wire? You mean how it, have I considered if the torsion
Like the
constant will change?
tension will change, the tension of the wire will change.
Tension, because we were using fishing line, so it's relatively cheap, so we can switch it out after every experiment.
After every experiment.
Yes.
Then do you consider about like when you get a line, then it's accurate enough. So how do you like choose a line?
Choose line. We assume that if the length is constant, or the line is constant, then the torsion constant should also be constant.
Okay, so there will be some sort of like some phenomenon that the line isn't accurate enough when you do your experiment. You wouldn't notice that.
Oh, we change different lines. For example, if you use stitching line, then the torsional constant wouldn't be a constant. So we actually experimented with various types of lines to get the one with the most constant torsional constant.
Okay. And it's up. So it's the time for the opponent to summarize the discussion.
Okay, so the report did a great experiment that it analyzes the torque and all the phenomena with graphs and functions. Okay, and I asked about the group disturbance is fastest and external intelligence the effective torque, and he took the height as parameters, so he can pick about the fast phenomena that caused the experiment, and the measurement of the torque on a turbine during the experiment, and different kinds of spiral, and actually different kinds of spiral of the torque really rotates and changes, and I believe that the reporter did great on like changing the experiment setups to assure its constant. Okay, and that's all. Thank you.
Okay. Thanks for the reporter and the opponent's great discussion. And here are some questions for both reporter and opponent. First, I want to ask the reporter, can you describe the flow inside the turbine?
Turbine, inside the turbine. No. So you mean the flow after the air connects the turbine?
Yes.
It is turbulent, so it is very difficult to calculate.
Okay, thank you. And the next question is, how you define the terminal velocity?
We define the terminal velocity. We use track to track the rotational velocity, and when its angular velocity doesn't change, then it tells me that it has reached its terminal velocity.
Okay, thank you. And can you say again that how many forces are there on the spiral?
There are two forces. There are three forces. First, there's torque from the candle, and then there is the torque from the string we attached it to, and there's also drag from the air resistance.
Okay, thank you. And so, do you consider the pressure difference?
You mean the pressure difference?
I think the convention given by the candle will give the pressure difference.
Oh yes, the pressure difference is a result of the impulse of the air molecules. So that is in our consideration.
Okay, and I want to ask, opponent, do you have any comments on this part? How to calculate the pressure difference?
difference, and I believe that I calculated by this the velocity of how it's spinning, and like how big or small like we cut this part, divided into the megapart.
Okay, thank you. And I want to ask, do you consider energy loss?
Do you consider energy loss? No, I think we don't really need to consider energy loss here, because after the current hits the turbine, it turns into turbulence, but we only need to determine the torque. And the relationship between the energy and the torque isn't so clear, so we didn't consider the energy loss.
Okay, thank you. And I want to ask that, can you please turn to page number 19? Why is the graph irregular?
Oh, why is the graph irregular? Oh, so this is the distance from the candle to the center of the spiral. So you can see that as the it reaches the maximum for this set of parameters at 1 to 2 centimeters. But when it is further from the center of the spiral, the torque actually decreases. So the rotational velocity decreases as well.
Okay, time is up. So it's the time for the preparation of the viewer. So it's the time for the reviewer.
Hello everyone, I'm Diana from Typt High School, Team Choseta. And today I'm going to review problem number 13, Kendall covered turbine. So here's the main focus. Which spiral turns the fastest and why? The test requires an optimization of the torque. The torque and rotation speed depend on each other, and how can the torque on the spirals be measured or estimated during the test? Can the torque exerted on the spiral be calculated depend on its parameters and some characteristic of the candle used? Which external influences change the effective torque, and with which spiral can this be maximized? So this is a summary for report. For the understanding of the problem, they talk about the turbulence and angular velocity. For theoretical analysis, they focus on continuity and momentum energy equation, and they use the ideal condition of the motion. For the experimental confirmation, they focus on the distance between the spiral and the candle, width of the spiral. Also, they say that it is associated with the flow, and they mathematically control the shape of the turbine and the laminar flow, and they also quantitatively explain the motion. And this is the pros and cons for the reporter. First, they give clear explanation of data and phenomenal explanation. Later, they gave us clear definition of problem statement, and the theoretical breakdown is very detailed. They know the experiment very well, and they give clear, short answers. For the count, I think their experimental results in graph are not clear enough, and the comparison between the theory and the experiment data is not enough. Also, we don't know how they actually set up for the experiment, and their variables are not enough. This is the summary for the opposition. I think they need to explain more on experimental data in graph also, but I think they have already got enough physical explanation. And this is the pros and cons for the opponent. First, they ask clear, short questions, and they understand the experiment very well, and they use the time very sufficient, and they give legitimate questions asked on further understanding of the theory. Also, they focus on what the reporter said, but I think they lack of comments for the reporter. And this is a discussion that we have discussed before. First, the opponent asks, can the reporter get the number from the equation on page 7? And the reporter responds that they just explain the relationship. And I think that the reporter can set the model to compare the theory and the experiment. Later, the opponent asks that can the reporter control the power of the candle? And the reporter said that they use the same candle, so they do not consider that, and I agree with the reporter. This is the next discussion. The opponent asks that what's the shape for the spiral? And the reporter responds that they just use a regular spiral, and I think that they can use arithmetic spiral, and that will be easier to calculate its radius. And let's move on to how to analyze the force on a spiral. And the reporter just drew on the blackboard, and I agree with the reporter. And they also asked that will the length of the candle change? The reporter says that the time is so small that the change of the length can be ignored, and I really agree with the reporter on this part. For the next question, they asked for the tension of the line change, and the reporter responds that it is constant. So I have asked them that how to describe the flow inside the turbine, and the reporter said that no, it is hard for them to consider. And the next, they asked how they define the terminal velocity. The reporter answered that they observe the motion, and when they become stable, thus they define the terminal velocity. And how many forces are there on the spiral? And the reporter answered 3.
Okay, the time is up. So it's time for the concluding remark for the reporter.
So we would like to make some clarification of our experimental conditions. So to control our experiments in the airflow of the environment, we place our candle in the corner, we close the door so that there will be no airflow from the door, and then it's placed into a box. We also control the wick length, which controls the power from the candle. And yes, as you can see, that is our experimental setup. And to answer the reporter and the reviewer and the opponent, the spiral is suspended by a string, and the string is chosen for the optimal rotational constant. So the rotational constant cannot be too large because the spiral will then spin too slowly. So we actually switched out several types of string, and fish line matches our needs the most. And we cannot analyze the turbulence inside the turbine because it is very, very complicated, and we thought if we did so, it would over-explain our phenomenon. So, but we discovered that if we place the spiral inside the turbulence section, it actually provides maximum torque because there's an airflow. And the airflow expands, which provides more torque. And finally, the mathematical analysis tells us what parameters will affect the torque. So we control these factors, such as the wick length, and we also use the aluminum wire to keep the shape of the spiral. So we agree with the opponent that we do not apply these mathematical analysis because the numbers are really hard to get, and it's very ideal, but it tells us what we need to control. And for example, it identifies that we need to control the normal vector of the spiral, which we did with our aluminum wire. Thank you.
Okay. So it's the question time for the jurors. Please about. Yeah.
Okay. I want to ask some few questions. Can reporter go to page number 8? Yes. Next one.
Next one.
7.
Yes, this one. Okay. So what I want to ask is do you find some best angle for alpha? That's the paper, okay? For small alpha to large alpha, can you find any best optimal alpha such that the rotation is the best? Top is biggest. Okay.
Yes, we think you can find the maximum alpha, but we did not change this parameter. We did not change it.
How about component? How do you see? Is this best optimal alpha exist or not? Or can you see that?
Yeah, I think it exists, and I think
Do you have the data for alpha?
No, we didn't do the experiment.
How about you?
I think it will be, but it is hard for us to get that from the experiment.
Can I elaborate? We think there will exist a the best.
Do you measure?
Oh no, we did not. Okay.
Okay.
Yeah, I just need to check again your data number at page 17, 18, they are similar. So for example, this one, okay, fine. You have an error bar on the data points, right?
Yes.
So how many times of experiment you did?
For each experiment, we conducted 5 tries.
5 times,
Yes.
okay. So this, you did the experiment with a different distance, and each distance you did 5 times? Is
Yes.
that right?
Yes.
Okay. And now go back. Yeah. On the right figure, yeah. Did you convert the right figure from the left? Or
Yes.
How did you do that?
Oh, we did this with this equation right here. Because
Okay. Fine. Now fine. That's fine.
okay, okay.
Thank you.
So, yeah. So, Dr.
Also, when the candle is burning, so the vents could shrink, right?
You mean the
So when you measure the torque, so you need to take some time to see the spiraling, right?
yes.
And then, but during the time, the candle can the length of the candle can shrink, can be shorter. So did you consider this parameter?
Yes. But we did not consider it because it is very small. To elaborate, the time we did the experiment is for about 1 minute, and the length that changes for the candle is about 1 to 2 millimeters, so it's very small.
Okay.
So, is there any further question? Dr. No. Okay, then let's start to score. So the score for the reporter A7887. The score for the opponent 6, 7, 8, 6, 7. The score for the reviewer: 7, 7, 8, 6, 7. Yeah. So let's take a break for 10 minutes. The opponent please challenge the reporter for the question.
We want to challenge problem number 11, false non-electric gap.
Problem 11. Rejected. Yeah. 11 rejected.
Okay.
I want to challenge tennis ball tower.
Tennis ball power.
Number 6.
Yeah. Number 6. Question number 6. Tennis ball power.
We accept.
Accepted. So the question number 6, tennis ball power. So please write down the name.
就没有。刚刚队长过来说确认一下。
the reporter please tap the forward.
So this is our report of tennis ball tower, and we are team Tesla. And here's our task. So build a tower by stacking tennis balls using three balls per layer and a single ball on the top. Investigate the structure limits and the stability of such a tower. And how does the situation change when more than 3 balls per each layer, should the number of balls on the top layer are used? And so we have to talk about the force structure and about how many layers we can build. Okay, so observe the phenomenon. So here are the pictures of the tennis ball tower. And our opinion is what is the tick equilibrium. And then if an object or system is subjected to multiple forces, if the resultant force of these forces is 0, so the torque to any point is also 0, so the structure can be safe enough. And the torque and the velocity of the object or system is also 0. An object or system is constantly equivalent, so it can form a tennis ball tower. Okay, so here are the parameters. So first, the coefficient of friction between the ground and the tennis ball. And second, the coefficient of friction between the tennis ball and tennis ball. And three, the tennis placement structure. So here are the parameters we have to consider. And if the coefficient of friction on the ground is less than the coefficient of friction between tennis balls, the ground will first exceed the maximum static friction and slide. So if on the contrary, the tennis balls will first turn into dynamic friction sliding. Because tennis is in necessary conditions, so we can only change the ground friction. And so here's our experimental design. So here are 3 layers of the ball. And red is the first layer, so it's the lowest layer. And white is the second layer and goes the third layer. Okay, so here's our experiment. Okay, so the main mass in the tennis ball is about 57.7 grams. Okay, so here's how we analyze our force figure. So the entire tennis tower has a strong symmetrical structure, so it can be used to draw the horizontal component of the force of the third layer of the ball on the second layer of the ball. And here's how we analyze force figure. So the vertical force balance and symmetry of the first layer can be obtained. So A0 times cosine theta n plus FO times sine theta equals 1/3 of mg, and this for 3 balls. Okay, so here's how we analyze force figure again. So take A as a float length and R is a radius. So as the picture in the left, and so n0 times d times cosine theta plus phi, and equals mg times d times sine theta, and equals FO times R plus d sine theta. And this is the function. So n0 times cosine theta plus FO times sine theta equals 1/3 of an mg, and n0 times d times cosine times cosine theta plus phi, n plus mg times d times sine phi equals FO and R plus d sine phi. So here are the FO and NO and the MU minimum. So the mu minimum is √2, and we have an equation that FO equals NO times mu. And the minimum friction coefficient that constitutes a 3-story tennis tower is √2. So here's the stability of the tennis tower at any layer recursive. So the force of the third layer of the ball torque at A, the A ball over there, and mg times d times sine phi equals 2 times phi n minus 1 y and d cosine phi. And here's the equations. We can get it from the triangle and the structure. But the horizontal force balance over here is Fnx equals √6 over 48 mg. And there's a vertical force balance, and which is Fn minus 1 times c and plus half of mg plus Fnz over friction. So the second is initial conditions with page 10 and 12. So the vertical force balance on the second layer, NO times cosine theta times plus mg plus FO sine theta equals 2F1z. So horizontal force balance of the second layer, NO sine theta minus FO cosine theta equals 2 times F1y sine theta minus 2F1yx cosine theta. So F1z equals 2/3 of an mg, and F1x equals 48, and equals 4√2 times 46 over 48 mg. So the force of the lowest layer of the ball. So we can define the forces on the layer. So we can see in the picture, first layer, second layer, and third layer. So torque at B 2 times F n minus 1 Z times D sine theta equals 2F times F n minus 1 Y times R plus D cosine theta. So the vertical force balance, the horizontal force balance, and Z direction force. And so here is the recursive, and we got a conclusion about F n minus 2Y equals root 2 over 16 mg. So here's our conclusion. The top walls are crucial for keeping the structure steady. It presses down on third walls and the low ridges turns press down on 3 walls on the table. And the counter reactions keeps the middle layer steady. Again, the friction is vital, so without it there will be no torque balance and the walls will roll away. Okay, so this is the end of the presentation. Thank you very much.
So, the question time for the proponent.
Okay, thanks for the reporter's presentation. And first, I'm going to ask, have you observed any gap between the principles?
What do you mean gap?
There's maybe some room between the principles.
So actually, the room between tennis balls are actually the same, so we can consider that as a room because, like, 3 of them and 3 of them in the top and another layer, so they would be together as a form of a strong structure. So we can consider that.
Okay. And what is the next layer have you stacked?
We have built it up to 10, but it's only like for a few seconds, but we got it up to 10 layers.
And the problem statement says that you have to investigate the stability. And do you think that the 10-layer tower is stability?
Yeah, I think that the tower will go is steady, and I believe by breaking down forces, then we can clearly know like how we calculate the parameters.
Okay. And have you considered the moment? The moment on each bolt.
The moment on each
the torque.
Torque of each bolt. So you mean a steady part or after releasing the top?
In theory, just if you consider the moment
okay, so I think you mean that I think torque only happens when the whole structure falls apart. So when it's a steady structure, it only goes down with the forces itself.
So have you investigated the different numbers of bolts per layer?
We only use 3, so.
Okay, thank you.
Thank you.
And it's the time for the preparation of the proponent.
Hello everyone, this is Jason Lee from Data, Teacher High School. And I'm going to post problem number 6, Tennis Tower. And here's the problem statement. Build a tower by stacking tennis balls using 3 layers per layer, 3 balls per layer, and a single ball on top. Investigate the structural limits and the stability of such a tower. How does the situation change when more than 3 balls per layer and suitable number of the balls on the top layer are used? And in the next opposition, we'll mainly focus on what causes the structure to have the stability and the maximum limit, and to find the maximum force to hit the bottom of the tower without collapsing. And how many layers can a tennis tower stack up to without collapsing? And here's the structure of the reporter. First, they give a video on their observation and to see if they see how does it collapse. And they give us some pictures of their theoretical model, and their setup is a bunch of tennis balls. And from their experimentation, we can see that they have investigated the coefficient between balls and the ground, and they analyze the force figure. And to their conclusion, they think that the top ball is crucial for the tower to be stable. And here are some strong and weak points for the reporter. And first, they give introduction to the problem, which is very clear. And they use analysis of the force to quantify the results, and experiments to verify the theory regarding coefficient between the balls and the balls, and the balls and the ground. And there are some weak points too. First, they miss the address of the physical phenomenon, which is the reaction force, and the lack of investigation on the energy and their actual stability. And they didn't do some experiments on their stability and the difference between each ball. So here are some questions I'm going to discuss about. First is there any way to block the influence of external factors? And second, how to make sure every tennis ball has the same coefficient of the friction? And what is the factor that restricts tennis from continuing to increase the number of layers, and whether it is possible to increase the number of layers superiorly by tennis through external factors? And number 4 is excluding the influence of external factors. Can you quantitatively calculate the maximum number of layers? And do you consider the friction of the floor, and does the ball touch the ball in the same layer? And next is about the theory. What is the factor that restricts tennis from continuing to increase the number of layers? And whether it is possible to increase the layers of numbers that superiorly caused by tennis through external factors? And have you considered the friction between the balls? Is the angle that you hit the ball accurate, and will it deflect? And how to quantitatively measure the strength of the force when you hit the ball tower? And do you consider the elastic compression between the tennis balls? And how is that associated with the experimental results? And what will happen if the degree of compression of each tennis balls is not the same? And how do you stack the balls? Is it accurate to stack by your hand? And I want the reporter to come discuss with me. And first is, have you considered about the external factors, like the wind or the floor is not flat, or the horizon?
So actually, we did experiment on a table, and like we did it in a classroom, so like keep all windows and those shots, so we avoided like wind towards something else, and fences.
What about the angle of your floor?
We did it on the table, so.
So what is that?
Okay, we actually tested our table, so like poured water on the table, and we make the table steady enough so that
so it is
like the water won't flow in rows.
Yeah. Okay, so next question, next discussion is how do you make sure every tennis ball is the same coefficient of friction, or do you think that this can be ignored?
So I actually considered that, but I didn't think of like an accurate way to like make sure every tennis ball. So the thing we do like we bought all the tennis balls from the same company. So yeah, we did our
But
best.
I think in our opponent's opinion, I think that every tennis ball is different because it is not a perfect figure. And maybe you can just do more about the friction force and to average it. And then you'll get a more accurate value of the friction force. And so what do you think is the factor that has a height limit of the tennis ball?
You mean like the layers build up?
Yes.
Build up like. I believe it's about the the angle of the lowest layer. So like the force from the top. Like if it increases to a tip point, then the structure will be smooth from fundamental.
So do you think that the ball under will be strict? Or it will become smaller when there's a force pushing it?
Yeah, it actually becomes smaller, but when it becomes smaller, then the angle between the balls changes, so that the structure will be destroyed. So we didn't really consider that.
Also,
because like when the ball in the lower like it changes, so it means the angle and space between the balls like it increases, so that the structure is destroyed.
So, do you think that the friction between every layers is the same or is not the same?
No, the friction and forces from the lowest layers is definitely less more than the layers from top. So yeah.
So how do you support your opinion?
By the force, like a breakdown of forces, and from the mass of the tennis balls.
So can you draw a picture for?
No, but our opinion is actually like there are less balls on the top that presses the top layer. So there's more balls like pressing on the lower layer. So the force will different, so friction.
Okay, I'm agree with your opinion. And the problem statement says that the problem statement wants you to investigate the stability of the tennis ball tower. And what do you think is that means? Just what is the stability means?
So I believe that stability means for example, we can prove it by the further questions. So how tall is the abilities tower, and how can we keep our experience in a stable and the calculation of the coefficients.
So you think that when it is more easier to collapse, the stability is smaller.
More easier to collapse the tennis ball.
Yes. So why is the reason that it is easier to collapse?
So I believe that's also because of the layers of the tennis ball. Yeah, and about this, I think it's about the layer.
No, I think that it is because the friction between many balls is smaller when it gets higher.
Yeah.
But
so that's also because of the layer, right?
So I think that the layers is the main influence of the.
Yeah. And I believe that's one reason.
Yes, I think so too. And do you think that in theoretical points, how many layers can it be stacked?
So we actually did experiments like instead of
I mean is theoretical points.
Theoretical points.
How do you think that?
So we didn't do like calculations on theoretical points. Yeah, we didn't do like theoretical analysis on the layers, but we did like true experience. In our experiment, maximum is like 10 meters.
So what is the main reason that you cannot build it to the 11th layer?
I believe it's because of the layer.
It's the height. It is because of height, but
Yeah,
what is the height influence?
So the height like influences the force that's given to the bottom layer.
Yes.
So like when the force got to a point that the transport streaks so that the handle breaks.
But I think that when the ball strikes, the friction will become bigger.
Yeah.
So it will be more stable if you say like this. So how do you explain that?
Oh. I think I don't understand.
So I think that when the force given from the higher balls is become bigger, because there's an angle that is pulled out. So when the pulling out the force is bigger than the friction force that the cable can give it, it will become unstable and fast. Do you agree with me?
So you mean that like in the layers of the ball, like there will be a vector of force, like pointed outwards?
Yes.
Yeah, I think so.
So, well, have you test the stability of the tower?
What do you mean stability?
Like from the statement, you say that the structural limits and the stability of such a tower. So how do you think that you can do your experiment that on this?
Okay, so not that rapidly. I think I can go with the fan or something. Like there are different strengths of the wind on the fan. Right?
So
we can,
you're giving a force that's from the side.
Yeah.
Okay. Okay, I think this is a point, and I think you can try to move your floor, or just make it
move my floor.
just like there is a equipment called the earthquake simulator, and you can try to use that to control the stability, to define the stability of the tower. And also maybe you can try to make the floor try to control the angle of the floor.
Oh, so you mean like if you do it on the table, then you like put it off like the angles of the table?
Yes, just if that will. How do you think that the angle will influence the stability?
Yeah, but those balls are tennis balls, so like if the angle changes, I think it will slip. I think it's nothing to do with the structure of the tennis ball, but more of the morality of the ball itself.
And can I use the backboard?
Yeah.
Sure. So this is the advanced only 2 layers. How do you think that the force is on this ball?
So I think the force is given by
the direction.
It's a 3D structure, right? So the top ball that presses on the ball will over. So it's actually that it's 3 balls when it gives on the top. So there's 3 balls that is in the direction.
Yes. And how does the friction and from the ground?
So I believe that the mass of these balls they get the force to the ground, so they get it back.
Okay, the time is up.
Okay, from the previous discussion, I think we have an opinion that we should do something to test the stability of the tower, which is a missed point in the presentation. and we think that we can move those, we can control the floors and just move it and to test the stability. And we also have some discussion about the forces and the friction force on the point of the balls and the balls and the ground. And we think that it is kind of complex, but we can still get it. And when we can still get a trend when the layer is getting higher. And we both agree that when the layer is higher, the stability of the tower is getting smaller. And thank you. This is my position.
So the time for the reviewer to ask the question.
Okay, this is a reviewer from Team Miracle. I'm going to be reviewing problem number 6, tennis ball tower, for both of you. Do you think there is a theoretical limit, just to clarify, for the height of the tennis ball tower?
So we didn't do analyze SS2 in various ways.
So you didn't analyze the theoretical limit?
Yeah.
Okay, so just to imagine, do you think there is a theoretical limit?
I think there will be.
And do you think there will be a difference between theoretical limit and the situation in reality?
I think it shouldn't be because like it relates.
Sorry, can you repeat your answer?
Like I don't think it should be different because like the reality should relate to our theoretical.
But in your theory, did you consider the differences in size of the tennis ball, or the different surfaces, or different mass of the ball?
No, like we did it all in the same way.
So then why would you think the theory and the reality will match?
Like the theory of the mass like actually changes about how like the ball should be used in our experiments.
Okay. What's your opinion?
I think there's no layer limits when it's from theoretical point, but there is a high limit when it's the real condition.
Okay, so would you agree that maybe mass and size would be the reason why?
Well, I don't think the mass and the size will influence the friction, so I think it will influence the
stability. Okay. And from the problem statement, other structures, what other structures can be built? So what do you think about, what other structures can be built, do you think?
So we did experiment in like a three balls in a layer. So I think we can expand it to like 5 or 7.
Okay, so do you think there's a pattern for what structures can be built? For example, like odd number towers, like three ball towers type of.
Yeah, I think so.
Do you think so?
Yeah.
There will be a pattern? What's your opinion?
Well, I think that when the 3 balls are the most stable, because when it becomes 4 balls, the gap between each balls will become bigger, so it will become more stable.
Okay, you mentioned energy when you were discussing. Do you believe energy analysis would be useful in this case?
Well, it might be some help. It might some help.
It might be have some help.
Yeah.
What do you think those help are? How do you think we can apply energy analysis in this case?
Just when the energy in the tower is more, it is more unstable, I think.
But then how could you quantify the energy in the tennis ball tower?
Like the initial energy of the height and the friction.
Okay. My time is up. Now.
Preparation time for the reviewer.
I would like to start my review. I will be reviewing Tensball Tower. I'm John Xu from Team Miracle. And we believe the focus of this question would be the structural limits and the stability of the Tensball Tower, and also what's the situation for 3 balls and more balls per each layer. For the reporter, they demonstrated the phenomenon by stacking their tennis ball with 3 balls per layer. They explained the theory phenomenon with a theory of static equilibrium and also friction. And they experimented with 3-layer towers, and they built it up to 10 layers. For their pros, they had a clear demonstration of the phenomenon. However, they failed to answer the problem statement, which is very important. They failed to answer the stability of the tennis ball tower. They didn't calculate the theoretical limit, and also they didn't consider other structures. Sorry, technical problem. Okay. They had some unclear graphs, they had some messy layout of the presentation, and they did not consider torque in their theory, which is pretty important. As for the opponent, they summarized the reporter's presentation pretty well. They pointed out the stability, the compression, and however they missed the reporter's discussion on the friction of the ground, and also they had poor time control. For the opponent, in their discussion, he asked, are there gaps between the tennis balls? The reporter said, the gaps are the same, so we didn't consider the effect. The reviewer thinks that they should consider a less ideal setup, where the balls are not stacked together that ideally. The opponent then asked, how did you control experimental conditions? The reporter said, they made sure the table is flat. The reviewer said, the opponent should measure the individual variation of the tennis ball size. The third discussion was how do you think the friction of different layers is the same? The reporter said the friction is different. The reviewer think the reporter cannot verify his calculation on the friction of each layer. The opponent then talked about the quantification of stability and how to test stability. The reporter said they can't think of a way to quantify stability, and the reviewer agrees with the opponent's suggestion. Next, the opponent asked, what do you think stability means? And the reporter said, if the tower collapses easily, then the stability is low. The reviewer thinks the answer of the reporter is very vague. The friction definitely influences stability, but we think deformation should also be discussed. Lastly, that's the point missed. They missed the limitation for the stacking in theory. They missed the explanation for limits in reality, which would be different from the limitation in theory because of the difference in size, the mass, and surface, which is not ideal in reality. And also they missed the effect of torque in their theory. And they missed the pattern for what structure can be stacked. So they only consider 3 ball structures. However, the problem statement required them to consider other structures as well. And also they missed control friction, size, and mass of the tennis ball tower in their experiment. Also, they lacked elastic properties they lacked discussions on elastic properties of tennis balls. And lastly, they failed to explain the effect of these deformations. Thank you.
So the concluding remarks of the reporter.
Okay, so thanks for speaking of the opponent and reviewer, and like I have to assure that our experience is quite well, and like we can consider about the torque of the friction and how we can test the stability of the structure of our tennis ball, and yeah, I think that's right. Thank you.
Okay. Yeah, so then it's the time for the juror to ask the question.
Okay. I think the reporter the maximum player you can get is 10. So if you want to get 1 more or 2 more player, what did you do? Or this stuff on so getting more players.
We can increase the friction and we could increase the friction between the floor and the tennis balls. Yeah. And
So can you try to fix the button sweep? So you can fix the button sweep, right?
yeah,
Can you try?
I can try.
How about opponent?
And we think that we can use the tape to tie three boards together and stack it up, and then
You cannot do that.
so and we can cut the tape. We can cut the tape later, so we can ensure that there's less influence from our hands uncertainty. So maybe it is because the uncertainty is stacked by hand.
Okay, then if you don't get the next one, stay over here. And how about you?
Okay, we do not think the main cause of the instability is caused by the lack of friction between the tennis ball tower and the floor, so we wouldn't like tape them together. We think the main source of instability is the differences in size of the tennis ball tower. So it causes like the tennis ball tower to tilt when you like build higher. Because each tennis ball has different properties like size and the surface. So we think we will maybe control the mass and the tennis ball size.
Thank you.
Any question?
Oh, so just a question for our reviewer. So you mentioned about limitation for the staking theory. So could you comment on it? I mean, so what's let's say when we are building, if the size of the balls they are all the same, and then can we build this structure to infinity height?
We do not do that calculation ourselves, but from what they have said, they believe that the limit is there are no limits. So what they mean is like in theory you can build infinitely high. So I asked them to explain why we can't build infinitely high tower in reality.
I have a question for you guys. Can you define some method for stability? Some method to measure stability? Maybe
So from side forces, everything defined by the strength of the what I just said, like wind strength.
So for me, I think that we can use this earthquake simulator to quantitatively define the stability, which is how does the floor shake.
I agree with the opponent that that's one way of quantifying stability, and we have two other ways. One is like you can apply a force to the tower and see like a void in the tower and see if it like falls. And secondly, we can calculate like a friction is required for the top wall. Since the top wall is what holds the whole tower together, if you take the top wall away, the tower will collapse. So we can calculate the friction required by the top wall. So maybe if we need more friction of the top wall, then the tower is less stable.
Okay, so is there any further question? No. Then let's make the score. Okay. So the score for the three-quarter 7, 6, 5. Okay. The score for the opponent 6, 7, 7, 6, 6. The score for the reviewer 8, 9, 8, 8, 7.
Thank you.
Yeah, so I think the scores are all quite consistent. So I think we still have time. I think we can make some comment or some suggestion to the students. Yeah. 那我们可以讲中文。
我给李波者的分数比较多，所以你们应该可以再多做。